De Sitter space is a solution to the equations of Einstein's theory of general relativity that describes a universe with a positive cosmological constant, which is a term in the equations that represents the energy density of the vacuum of space. In this space, the expansion of the universe is accelerating, as if there is a repulsive force pushing everything apart. De Sitter space and fate of the universe is closely related to the concept of entropy, Boltzman brane, and arrow of time. De Sitter space is a mathematical model of the universe used in modern cosmology. The names De Sitter space and anti-De Sitter space honor Willem de Sitter, a Leiden University astronomy professor and the head of the Leiden Observatory. In the early 1920s, Willem de Sitter and Albert Einstein collaborated closely in Leiden to study the structure of spacetime. The far future of the universe seems to resemble something close to a De Sitter space, which is a special kind of space that expands forever without matter or radiation in it. The time one can have to wait to see if our universe will become a De Sitter space is so enormous that it is beyond eternity itself for all the practical purposes. Such timescales are vast, monstrously vast, on the order of 10 to the 10 to the 76 years, and it is so far away into the future that we humans simply cannot comprehend. Most physicists believe that the second principle of thermodynamics, which stipulates that entropy in an isolated system, such as the entire universe as a whole, can never decrease, and this has an impact on the irreversibility of the arrow of time. This has to do with the entropy term from thermodynamics, which is only tangentially relevant to how disorder is understood in everyday life, because the entropy will always increase in closed systems, according to thermodynamics. The reason for this is that minor differences are considerably more likely to occur in big numbers than huge differences, and the quick response to the question is that we have no idea, because the apparent existence of an arrow of time is one of contemporary physics' greatest unresolved puzzles. The future is unknown to us, but we can recall our pasts. Effects always follow causes, not the other way around. In a De Sitter universe, the entropy would have done it with everything that resembles as normal matter by our standards, and by that time, everything in the universe will be characterized by very low energy levels, radiation only, and very long time scales. Occasionally, electrons and positrons drifting through space will collide to form positronium atoms. These inherently unstable structures must inevitably disintegrate into their component parts. Very slowly, additional instances of low-level annihilation will occur. The De Sitter universe is a desolate, barren, cold, infinite void, and it is characterized by its high degree of symmetry and is homogeneous and isotropic, meaning that it looks the same in all directions and at all locations in space. And it is also a maximally symmetric space. Its geometry completely determined by its curvature. De Sitter space plays an important role in modern cosmology because it is believed to represent the late-time evolution of our universe, when the expansion is accelerating due to dark energy. It is also used as a background space in many theoretical models of physics beyond the standard model, such as string theory and inflationary cosmology. The latest observations suggest that our universe is currently undergoing accelerated expansion, which is a key feature of De Sitter space. This acceleration is thought to be driven by dark energy, which behaves like a cosmological constant in Einstein's theory of general relativity. It is commonly assumed that our universe is approximately described by a De Sitter space, but the actual geometry of our universe is more complex than that, and it has a non-uniform distribution of matter and energy, which creates fluctuations in the cosmic microwave background radiation. These fluctuations provide valuable information about the properties of the universe, such as its age, composition, and geometry, because one of the properties of a De Sitter space is that it is infinite in size. We simply don't know if our universe is finite or not, because the observable universe's size and scale are determined by cosmological horizons. Despite the real possibility that our universe is infinitely large. According to the widely accepted Big Bang theory, we can only observe a small portion of it, which are distance restrictions imposed by cosmology. Our universe's cosmological constant is positive, but because we also have mass energy, the attracting gravity caused by the latter is resisted by the repulsive gravity caused by the former. So our universe's expansion will either be accelerating or decelerating. The density of mass energy, or the quantity of mass energy per unit 3D volume, determines its impact, and even if the cosmos is expanding, the overall amount of matter and energy does not change. The cosmological constant seems to remain constant over time, and its impact does not lessen as the universe gets bigger. In de Sitter space, the universe expands exponentially, meaning that the distance between any 2 points in the universe increases at an accelerating rate. Data from various sources all support this theory. These sources include the cosmic microwave background radiation, the finding of early universe baryon acoustic oscillations, and projected abundances of primordial elements, the so-called Big Bang nucleosynthesis, as well as supernovae brightness with distance, the redshift variation. It is possible to model the cosmological constant as a peculiar sort of mass energy with positive mass but negative pressure. In other words, we replace the cosmological constant term in the Einstein field equation with a mass energy term with these peculiar characteristics. This mass energy term is sometimes referred to as a dark energy because it appears to be caused by a certain form of unknown mass energy. In contrast to matter density, dark energy density does not appear to alter over time as far as the available data can tell. This would be a property of the vacuum that one would anticipate, that shouldn't alter as the universe expands and the density of the material within it decreases. This is another factor that leads many people to believe that dark energy is a vacuum phenomenon. The spacetime known as de Sitter, which bears the name of its discoverer, is described as having no matter, either ordinary or dark, but a positive cosmological constant, or dark energy. It is an empty 4D universe with positive curvature because of the cosmological constant. The space expands at an exponential rate due to this positive curvature. It is devoid of all kind of matter, but exhibits a distinctive and peculiar behavior in space and time. The curvature it creates is the same everywhere, because the cosmological constant factor in the Einstein field equation is constant everywhere in space and time. It behaves like the 4D hypersurface of a 5D hypersphere, and it is maximally symmetric, and the curvature is uniform throughout. One should not refer to our universe as a de Sitter universe, since the de Sitter space lacks mass energy while our universe contains both. Our vacuum, which has no mass, can be described as a de Sitter vacuum. Though it isn't technically accurate, the term de Sitter space is frequently misused to refer to our universe. Keep in mind that as the cosmos ages, its matter will eventually become so diluted that its influence on curvature will almost disappear. At that point, the cosmological constant effect will dominate the universe's appearance. In essence, we are heading toward a universe that will resemble a de Sitter universe in every way. As time goes to infinity, our universe asymptotically approach to be a de Sitter space. Although in cosmology, we typically refer to the 4D spacetime of our universe when we talk of de Sitter space, mathematically, we are not constrained to 4 dimensions. In other words, we can think of de Sitter space as existing in 3D, 5D, 6D, or any other number of dimensions. In these situations, we often define the space in terms of its symmetry rather than a cosmological constant. It is similar to the hypersurface of a hypersphere, where, in an abstract sense, we can imagine the hypersurface as always being a radius-like distance from a center point, similar to how the surface of the 3D sphere in our experience is everywhere equal distance from the sphere's center. To give you a strict answer, in mathematical physics, n-dimensional de Sitter space, often abbreviated to dSn, is a maximally symmetric Lorentz manifold with constant positive scalar curvature. It is the Lorentz analog of an n-sphere that have canonical Riemannian metric. It is, in short, an open-like universe that expands forever. It is what our universe is believed to be in the far future.